Okay, very good. So before we start with the afternoon talk, we have mics, which would be nice to use for asking questions so that everything gets recorded nicely. So when you have questions, you raise your hands, and if it's a short one, maybe no, but if there is a little bit of debate and discussion, it would be nice to remember to use the mic. That's the only comment. And so with that, please take the hint from the previous talk in being as open to interaction and questions as possible and to the diversity of the audience. And so with that in mind, Yorgo Pano will tell us about celestial OPEs, W1 plus infinity and beyond.
Great, thank you. Thanks for the chance to speak here. So what I'm going to talk about is an ongoing project with Prahar Mitra and Andrea Poom. So yes, please don't hesitate to interrupt at any point if you have questions, and then I can write on the board, which is nice. So I'm going to start at the sort of more basic level and then discuss what we're working on. So of course, as a motivation, we know, and especially in the ADS case, that the holographic principle has proved to be a useful tool to study quantum gravity. And this was especially well understood for negatively curved spacetimes, namely in ADS spacetimes. So a natural question would be to ask if this can be extended to asymptotically flat spacetimes. And for this, there are two approaches. The first one being this Carolian holography, where you take the dual of Ethereum asymptotically flat spacetime to live on the Scry plus, which is the boundary at null infinity. And Yannick had a lecture about this last week. And the other approach is celestial holography, where you have like a codimension 2 dual theory, where it lives only on the celestial sphere at null infinity. And Tim had a lecture about that last week as well. So in this talk, I will focus on this latter approach, so celestial holography. And for this, I would like to start with setting the stage with what I'm going to be working with. So let's say you have a scattering process in 4 dimensions. So particles P1 and P2 coming in, and particles P3, P4 coming out. Then this process can be described by the scattering amplitudes, where the asymptotic states, so the scattering amplitude is defined by the asymptotic states, and the asymptotic states are taken to be in a momentum basis. So this object has manifest translation symmetry through the presence of the momentum-conserving Dirac delta. Now we can express the asymptotic states in a different basis, namely this boost or Lorentz basis, and then we would have an object that would transform covariantly under Lorentz transformations. And since the Lorentz group in 4 dimensions is isomorphic to the conformal group in 2 dimensions, then the analogous object that we would get would transform covariantly under the 2-dimensional conformal group. And this is what I'm going to call the celestial amplitudes. And for massless particles, this change of basis can be achieved through the Mellin transform, which I denoted here. Now, we can parameterize on-shell momenta by 3 variables, omega, z, and z bar, where omega is the energy and z bar can be identified with the positions on the celestial sphere. You can see the Mellin transform sort of trades out the energy label for a different label, which is the conformal dimension of the operators on the celestial sphere. And so with this change of basis, a lot has been achieved in the last decade or so. Namely, the most important would be the relation between universal IR behaviors, which are soft theorems, and sort of giving them a symmetry interpretation and relating them to asymptotic symmetries. And with that, we can even have local conformal symmetry on the sphere by constructing a stress tensor out of the subleading soft graviton theorem. So this kind of leads to the question, is there then a celestial CFT, namely a CFT that lives on the celestial sphere that is dual to asymptotically flat spacetime? Well, even though we've had some nice advancements, which I didn't, of course, cite all of them here because there are too many, the celestial CFT has sort of weird properties compared to the usual CFTs that we have. The first thing would be that it's a non-unitary theory in the sense in which we usually mean unitary in a CFT. So there has been works trying to like define optical theorems for celestial CFT, but they are in no way what we are used to in usual CFTs. And another like weird feature is that these the celestial amplitudes are distributional. So it has been observed by these first two references that they are distributional. Celestial amplitudes at lower points are distributional in the sense that they are depend on delta of z minus z, like they are distributional in the z and z bar variables. And they are also distributional, and we showed that in an earlier work with Majdouli Bourgi, in the conformal dimensions, because these when you take the Mellin transform of certain amplitudes, you get divergences, but these divergences can be explained in terms of distributions. And a lot of other things, which I'm not going to talk about, but all of this was to show that we need a better understanding of the celestial CFT and of the properties that define it, in order, if you want to have a fully fledged duality like we do, for example, in ADS. And that includes understanding the spectrum, the symmetries, etc. And one way we can go in this direction is to focus on the OPE. So what I mean by celestial OPE is the OPE on the celestial sphere, so of the operators that I showed you how to define earlier. And this can be, the study of the OPE can be achieved by Mellin transforming the collinear limit of the scattering amplitude in the momentum basis. And this can be easily shown because if you take the dot product of two momenta, this is proportional to the difference of the positions on the celestial sphere. So if P1 dot P2 is going to 0, then Z1 is going to Z2. And then we study the OPE. And what has been shown is that the leading splitting function in the momentum basis translates into the singular term of the celestial OPE. So in a, say we're scattering gravitons, there's a theorem that tells you how this amplitude behaves as two gravitons become collinear. And this is parameterized with the splitting function. Now, if you take the Mellin transform of that splitting function, it tells you the OPE, the leading singularity in the OPE of two graviton operators. Now, we have the OPE, as I said here, or the leading singularity in the OPE of two graviton operators. And what we can do is take the soft limit. And this is, so we take the soft limits of the two graviton modes. And by taking this double soft limit, we land on an OPE, which will eventually give us the W1 plus infinity, or that was discovered a couple, 4 years now. Yeah. Yeah. Yes, so I'm working, of course. So here I'm working in 2-2 signature. So Z and Z bar are independent. And I'm only taking the holomorphic limit in the sense that I'm taking Z1 to Z2, but keeping Z bar and Z bar 1 and Z bar 2 different. So as I said, first take the collinear limit, and then we take the double soft limit. And one question I would like to address in this talk is there an ambiguity in this definition of the W1 plus infinity algebra? Since we're taking two soft limits, does it depend on which soft graviton we're taking soft first? Because there has been known in the literature that some of the OPEs, namely the OPE of the holomorphic and anti-holomorphic currents in Yang-Means theory, for example, there is an ambiguity there. So if you take the positive helicity soft graviton first versus the negative helicity first, then the OPE is not, depends on the order of soft limits. So one thing I would like to address is that this ambiguity is here for the W1 plus infinity. And another thing I would like to address is this, is the following. So we have the leading singularity of the OPE, and the question is, what is the can we say something about the full celestial OPE, including the regular terms, I mean? So this would be interesting because these also tell us about the symmetries of our theory through the presence of like the descendants that we have and the spectrum of our theory as well. So for example, in Yang-Mills theory, so if you take the OPE, let's say of a positive helicity, let's say of these two operators, so one is, let's say, ZZ bar. So if you take the first operator soft, I didn't think this through. And then the second operator soft, delta 2 minus 1. So I'm taking the leading soft glue-on theorem, basically. So here I'm taking the delta 1 operator soft first, and then taking the delta 2 operator soft. This is different than taking the first one soft after the second one.
Yorgo, can you remind me? I thought there was a difference of status between this ambiguity in double soft, depending on whether you're on momentum basis or celestial basis. I thought somehow this was timed in the celestial basis, but maybe I remember.
No, they are really different.
Like
so yeah, so if let me just continue my equation. So, they are really different. So if you take the positive helicity first and then the negative helicity, you get something that's completely different than if you do the other way around. And it can be understood, you know, I don't know if you're following like Daniel's, Capet's interpretation is that you're moving around in the space of vacua. And if you go one way, it might not lead you to the same place that if you go the other way, for example.
And so if you do, I guess there is a prescription that gives W1 plus infinity in there.
Yeah, that's what we're going to see.
You're going to
This is what I'm going to discuss.
Okay.
Yeah, to see if there's this prescription to do that. Well, I can just tell you.
And if there is one, are you going to say what the other prescription
what's
gives?
the motivation?
And what the other...
Actually, like what it's going to turn out to be is that the commutator of two, so you can evaluate the commutator of the soft limits to evaluate the difference between the two. And what will turn out is that the commutator is 0. So there's no ambiguity in the definition of the W. Yeah. Sorry?
Yeah, so you mentioned that two limits, there's an ambiguity because the limits don't commute, right?
Yeah.
But then...
but that's something we didn't know, right? So it could be that this commutator was non-zero and that we would need a prescription to have like this W1 plus infinity.
Okay, so
we didn't know that, I mean...
Yeah, so I guess what that means is it's not obvious that they commute.
Exactly.
But it turns out that they...
Yeah, indeed.
So
it's not trivial.
So this is 2 plus 1 amplitude or plus 1 minus 1, I can read?
Plus 1 minus 1.
Okay, because usually the W infinity is in the same helicity sector, right? So here, okay.
But we don't know, like the prescription can still be preferred over that gives, like, because when we take the doubles, as we will see, when we take the double soft limit, we're taking one before the other, and this gives the W1 plus infinity.
But the plus plus is not ambiguous.
Well, this is what we show. But we wouldn't know that for the leading. Nobody has shown that for the leading.
Sorry.
For the W1 plus infinity.
Okay. So the plus, so I'm just trying to understand. Plus plus is not ambiguous, but plus minus.
For the leading gluon, no. But plus minus is.
Yeah, okay.
But what I'm saying is that nobody says that this should be the case for the entire tower of soft gravitons. No, nobody.
So do you agree? Would you agree that W infinity usually is the plus sector, and now you're looking at the interaction of plus minus, which is
no.
No, you're not.
Let me get to this part because I will get to it.
Sorry, just to, you said you're working in 2-2 signature?
Yeah.
Can you briefly comment on why?
Why? Because I'm taking this holomorphic collinear limit. This is how the W1 plus infinity algebra was constructed. Not taking the full collinear limit, but you sort of work in 2-2 signatures so that Z and Z bar are independent. So you can take Z to 0 without taking Z bar to 0.
So if you were in mostly minus signature, mostly plus, it would be similar to what the approximation Laurent was using earlier on, namely that you're just looking at some complex self-dual sector?
Yeah, exactly.
Okay, I understand.
Exactly.
Thank you.
More questions? Okay, so the outline of my talk will be the following. So first of all, we know that we have the leading and subleading soft theorem. We have a closed form expressions for those soft factors. And first of all, I want to introduce how we can define soft factors or soft theorems to all orders in the soft energy. Second of all, we will derive the W1 plus infinity algebra from taking double soft theorems, and we will discuss this order of limits where there could be an ambiguity, but turns out there's not. And third of all, I will discuss the full soft OPE, including the regular terms, and see what we have there. Yeah? No. Okay. So soft theorems. So let's take an amplitude, which I will write in the following way, where O plus 2, the plus 2 here refers to the spin of the to the helicity of the particle. So here it will be a positive helicity graviton. And say we're taking the energy of that positive helicity graviton to 0, then we know that the amplitude then factorizes into what is called the soft factors times the amplitude without the soft graviton. And so this is the Weinberg soft pole, and this is the soft factor that was discovered by Cacciazzo and Strominger. And in the Z and Z bar variables that I've introduced earlier, these soft factors take the following form. So Z bar and Z are the coordinates of the soft graviton, and Zk and Z bar k are the coordinates of the hard particles. And omega k is the energy of the hard particle as well. So good, and these are related to the BMS algebra in the following way. So if we define the soft operators as this, so we take our positive helicity graviton, and we apply this limiting differential operator right here. So you can see that this operator picks out a specific term in this soft expansion. So for L is equal to -1, you will get the leading soft factor. For L equals 0, you will get the subleading soft factor, so on and so forth. And these soft operators turn out to have a specific conformal dimension on the sphere, which is the -L, where L is this number that's appearing here, and spin +2. And the modes of these operators obey the W1 plus infinity algebra when obey the BMS algebra when L is equal to -1 or 0. So if you take the modes of the leading and subleading soft factor, these obey the BMS algebra. So a natural question to ask, well, is there a closed form for the soft factors to all orders in the previous expression that I showed? And this question was addressed in a paper in two papers, one by Hamada and Shu, and another by Li Lin and Zhang. And it turns out that if you project out a certain part of the amplitude, then we can write down a specific soft factor to all orders in the soft energy. So it won't be a soft factor of the full amplitude, but it will be a soft factor of a projected part of the soft amplitude. However, there was an issue because, yes, we could define these SLs where L can go from -1, 0, +1, etc. But they would include differential operators of the momentum in the following form. Now, these differential operators have no on-shell, well-defined on-shell limit. We can just try to do it because they are prescription dependent on how you go on-shell, so they're not well-defined. So one thing we can do is to continue these operators to the full angular momentum, because the angular momentum can be expressed in terms of derivatives with respect to the momenta. And then we can take the on-shell limit, and this is what they did in this paper. And we can recover the soft factor to all orders in the soft energy. Yeah.
So what is this completion to full angular? So then you say if I do this completion, then there is a well-defined
Yeah. So if you complete,
notion of
so of course the angular momentum operator has a well-defined on-shell limit. So if you complete, but this differential operator does not.
Okay.
So if you complete it to the full angular momentum, then you can take the on-shell limit.
And this completion is unique in some sense?
Yes. I mean, it's unique in the sense that I will. So these soft factors will reproduce the W1 plus infinity algebra. Yeah. Exactly. So this is what I was going to say. Yeah. But first, a question, yes? Yeah, sorry. Sorry? Yeah? This operator, yeah, it's not, no. With, yeah. Yeah. Yeah, so this is what I'm saying is that one completion is to take this differential operator to the to the full angular momentum. And that's one thing, like one way to do it. And then you can define this on-shell limit and express the soft factor in terms of the on-shell coordinates of the momenta, which are z, z bar, and omega, which is what's being done here. So indeed, the price to pay for this is this dependence on Z0. Because when we complete this this differential operator to the full angular momentum, we have to divide. So this is a technicality I did not want to get into, but I'll give you the full picture. We divide by this null tetrad vector, which has a reference point dependence. So then we get a reference point dependence in the soft factor, which is the Z0 that appears here. This is just a constant of L, M, and H bar K. And but the nice thing is that we have a sort of like full closed form expression for the soft factor. Yeah? Sorry? Yeah? It's related to your to the spin of the charges that you are defining. Yeah. Exactly. Equals +1. Yeah. Yeah. So that's a good question. Yeah, that's a good question. But then, so for L equals 1, you can see that there's no Z0 dependence. And for L equals -1 and 0, you can use global symmetry to get rid of the Z0 dependence. Global conservation. Like for L equals -1, you can use global translation symmetry to get rid of Z0 and global Lorentz symmetry for L equals 0.
So let's say if we look at M equal 2, which is supposed to be 3, then this operator becomes the inverse of D bar.
Yeah, so this is what I was talking about with like the relation to what you were saying, and then I can get to it at the end if you want, like tell you what my intuition behind what we were discussing is about. Okay, so now that we have a soft factor to all orders, what we can do is take the double soft limit inside of the amplitude. So if we first take this O plus 2 that depends on Z and Z bar soft first to some order in the soft expansion, so to order L, and then take the second one soft afterwards. So when we, yes. Yeah. So how I define this operator, how I define this operator is just the insertion of the soft factor that I showed before. So I'm talking about the projected amplitude. However, that's an open question, is because you see we have like a projected amplitude, which they defined in this paper, but then it wasn't well defined on shell, and we had to complete to the full angular momentum. Now the question is, first of all, can we define a projection operator that defines directly to this full angular momentum? And second of all, does these projection operators commute with the soft limit? Because here we're taking two soft limits, not one. So these are still open questions. And this is part of the outlook that I'm going to get to in the end. Thank you. So when we do this double insertion, so this is the definition of this soft operator, and then taking this primed sort of positivisticity graviton is this L prime operator right here. And so using the soft factors that I've shown before and expanding in Z minus Z prime, we land on the following form. So the leading part of this expansion is if you've been following this W1 plus infinity story, is exactly the OPE of the two soft gravitons that later gave the W1 plus infinity algebra, plus some regular terms which I did not write here. And these regular terms depend on the Z0. So you can see that the leading part in Z minus Z prime does not depend on Z0. Okay. So then, yeah, what I said is if you decompose these operators into SL2R bar modes, so basically these are the modes that correspond to each power of Z bar in this expression, then you get, okay, after some redefinition of the modes, you get the W1 plus infinity algebra. So the Z0 is contained in these regular terms. The singular term does not contain Z0. Yeah. All good? Okay. So let me recap what has been done so far. So we have a universal, we have like a closed form expression for the soft factor to all orders in the soft energy, which is this SLZZ bar. And if you take inside the celestial amplitude consecutive double soft limits, so you take one graviton to be sun, then another, then you get the W1 plus infinity algebra. Now, a natural question to ask at this point, does this prescription depend on which graviton operator I'm taking soft first? Like if I'm taking Z soft first, or the operator at Z first, or the operator at Z prime first, does this matter? So in order to see if that matters, we need to evaluate the commutator of the soft limits. And to do that, we need to evaluate this thing. I'm gonna spare you the detail because this is not trivial at all, how to treat this expression. you get some hypergeometric functions, and you need to like do nasty sums and stuff like that. But in the end, what you get is that this commutator vanishes. So if you take the first graviton to be soft, then the second, is completely equivalent to taking the second soft first, and then, yeah, you get what I mean. Yeah.
Because here you're somehow going back and forth because between the momentum basis and the celestial basis, and you see, I thought there was this ambiguity dropped out in the is well known in the momentum basis, but that in celestial basis something.
Well, these soft
happened.
operators are inherently boundary operators, right? So if you take this limit, you get a boundary operator of a specific conformal dimension. So it's like it's this definition right here. When you take the soft limit, you get an operator that lives on the boundary. Of course, like here I'm writing 2h bar, k, which is like in the celestial basis, but my definition of 2h bar k is the momentum space one. Well, they're completely equivalent. Mine.
Sure, but I thought in the limit, precisely there was something special about taking these limits in the momentum basis versus the.
Are you thinking about a specific paper, or we can you can let me know? Yeah, that would be interesting.
But so at the end there is no ambiguity. That's the upshot.
So in the end, the W1 plus infinity algebra is ambiguity free in terms of which graviton operators you take soft first. Show what? Sorry.
When you say zero, you mean the regular term, just you mean there was a singular term, the regular term, so you mean the regular term dimension?
This zero? Yeah. No, the full thing. To all orders. The full thing vanishes. Yeah. So indeed the OPE, the singular part plus the regular term is free from ambiguity. Indeed, yeah. If you use different Z0s, that's something we tried. That's not true. They don't commute.
Is there a meaning of non-commutation?
For different Z0s, so in general, when two of these soft operators don't commute, so that's, yeah, as I said, like something that Daniel Capets was working on is these, it's something actually that came up in your talk, is that you define this algebra and you have basically infinitely many on Scri Plus because they differ from one another by a soft, like soft graviton basically, because the value of the shear is not the same, right? So this ambiguity can be related to the fact of having non-trivial curvature on the space of vacua of the CFT, of this, like, manifold of CFTs that you have. But what it means when Z0 and, like, if you take two different Z0s, that I don't know. We were hoping that it would work out for two different Z0s because then we could define the projection operator to get the soft factor using the Z0. So because if there are two, then the projection operator commutes. But that turned out not to be the case. So, okay, other questions? Okay, so now that we've shown that this amplitude is free from ambiguity, what we want to do is study these the regular terms that appear. So we want to look at the full celestial OPE. And as I said, the regular terms here depend on Z0, on this reference point. But of course, if I take the LL prime to be 0 or plus or minus 1, this is what Laurent was saying, then the Z0 dependence drops out because of global symmetry. And the regular term takes this nice form right here. Now, I will only study this because I don't have an explanation when Z0, like for the more subleading operators. So I will be looking at the full soft OPE when there is no Z0 dependence, namely for these first three modes, these first three soft operators. So it turns out that you can sort of manipulate this expression, and that the full soft OPE for L and L prime in 0 plus or minus 1 is the following. So you can look at the singular term. This is, well, I've already shown this. So this is the W1 plus the operator product expansion that gives the W1 plus infinity, and this was what was being discussed before. But then the regular terms give us these contributions. So you can see here appearing the holomorphic descendants of these operators. And you have also this normal ordered product of these two operators that appears as well in the soft OPE. Yeah. Yeah, these are the first three, exactly. This is not the projected amplitude. Yeah, this is, the projection, of course, is not unique. Like, I think, there's one projection that gives you the W1 plus infinity, and it's the one I told you about, is this, I don't know, like, if there's a projection interpretation to it. That's why I said it's still under investigation. So we're looking at if we can define a projection operator on the amplitude that would give us exactly these SL, these self-factors that I told you about. Yeah, the first three soft factors, the universal ones. You can expand, and then you expand and you try to look at the operators that appear, and so this is the full OPE. Yeah, indeed. For L prime and L plus L prime and 0 plus or minus 1. So one thing to note here is that while we have these global SL2, the holomorphic descendants appearing, there are no Virasoro descendants. So that's one thing we were kind of surprised by. And then, yeah, I don't know, because I don't know if there's a way to sort of, because celestial CFT has more than, usual CFT, in the sense that we have also super translations. So in a way, we should be able to, the descendancy structure should kind of reflect that, and that we would have the super, like, BMS primers, and not just, because here we're studying only on to these global SL2C primaries. Yeah, so I don't know if, like, when we study with the Z0 dependence, so the full OPE, that we will get something that are BMS primaries, but okay. Yes?
Just to remind me, for me, it's in agreement with what I was saying. It's like the symmetry that controls the OPE is not Virasoro. It's really W infinity algebra, which is, and what we should do is, not just copy. We should study the OPEs of this W infinity, which, we cannot just take it from textbooks, but they must be as powerful as the Virasoro ones. It's another localization of SL2C. It's not the one we're used to. And, but that's really the gravitational one. I know that goes against a little bit the grain of where it was started, but
so the celestial CFT,
it's not a, it's
not like a usual.
Could you just repeat, Yorgo, the statement about Virasoro descendants? I missed what you...
So in a theory where you have like not just global SL2C symmetry, but Virasoro symmetry, so you would have like descendants that are L minus 1. So you have a primary operator O, delta and L. And what you have is the global descendants. So you have L minus 1 to the n, so it's n order. But you also have, at a certain level, so level 1, you only have L minus 1 on O. At level 2, descendant, I mean, you have L minus 1 squared, L minus 2.
Yeah, this is just, yeah.
So what I'm saying is that in this OPE, only these appear. So they only have L minus 1, which is basically the holomorphic derivative, this del I plus 1. So you can see here that we have this operator appearing, and in this finite piece, you have this del I, the same thing with the del I plus 1. So it's the global holomorphic. So it's like these L minus 1 to the n. But there are no L minus 2.
Oh, wait, so you say in the regular part of the OPE, you would
Yeah.
have expected the other,
To have
the,
also
or the
the-
full catch,
Yeah,
catch
to have
table,
all
or whatever.
yeah, exactly. Yeah. Sorry.
So the staking is that it's going to close. But if you take L, say L and L prime equals say to 1.
No, I'm excluding that. I'm excluding that.
You are excluding this case.
Yeah, L prime and L plus L prime in 0 plus or minus 1.
Okay, so the three conditions are imposed at the same
Yeah, yeah. So, yeah, you can choose L and L prime such that these three things are in 0 plus or minus 1. Because at L plus L prime, if you choose L and L prime to be 1, then you get L plus L prime to be 2. So the operator here will be minus 2, which has non-trivial Z0 dependence. And here I'm only discussing the operator product expansion where there is no Z0 dependence, when the Z0 dependence drops out.
Okay, but then you are looking at the subset of the OPEs along these operators.
Yeah. I'm only looking at the leading three minus the L plus L prime, L and L prime goes.
So there is no truncation. So L1 plus L1, so plus 1 is plus 2.
Exactly.
No mention.
Yeah, exactly. Yeah. Okay. So this is what we get. Yeah, I think this is was all that I wanted to say. So let me summarize. So first of all, we saw how we can define soft factors to all orders in the soft energy. And then we saw that by taking this double soft insertion, the singular term gave us this, the singular term in the OPE that gives one W1 plus infinity. And the regular terms, we were able to identify them, and they include these global holomorphic descendants, as well as this normal order product that appears. And we have also shown that in defining this W1 plus infinity, there is no ambiguity in the sense of which graviton you take soft first, because the commutator of the soft limits commutes. And I wanted to finish with some open questions, which there's a lot of them. So yeah, first one would be, can we derive the OPE for all of the subleading operators, not just L and L prime and L plus L prime in 0 plus or minus 1, but for arbitrary L and L prime. So this is, under construction. So what does this, also the symmetries interpretation of these OPEs, like what are the descendants that appear, etc., as well as the projection operator, which questions were asked about that. But also, one interesting thing would be so here we're taking the OPE of 2 positive helicity gravitons. Of course, it will be completely equivalent for 2 negative helicity gravitons. And the interesting thing would be to take the mixed helicity commutator. And what we expect is that the commutator will not vanish. just like it does not vanish here. And it would be nice to relate the non-vanishing commutator to the space-time charges that we saw this morning in Laurent's talk. Because you can see that if you, the soft charges, the full soft charge is the sum of the positive helicity soft graviton and the negative helicity soft graviton. So if you want to commute two charges, since the commutator of two soft gravitons, positive helicity soft gravitons, are 0, and the commutator of two negative helicity soft gravitons are 0, the only thing that's left is the commutator of the plus and minus helicity gravitons. So this will give a non-trivial answer, and this, I guess, will be related to the, to the construction of the charges that's using the covariant phase space formulas and whatnot. And that's it. Thank you.
So more questions?
Okay. Andrea, you have?
Questions for more
Andrea?
shyer
Massimo? Andrea, you had one?
Can I? About the Virasoro story. But on the other hand, so somehow looked surprised about the fact that there is no Virasoro. But you also worked in NED for other stuff, no? And there you don't expect any Virasoro at all, no? Could it be related to the fact that this mechanism should hold in any dimension?
Sorry.
So I mean, you are talking about the universal part of the soft theorems, and these
Yeah.
exist in any space-time dimension. So do you expect this structure to be similar in any space-time dimension? Because this may explain why you don't have the Virasoro part, or say in the case that if you are in 6 dimensions, you cannot have the Virasoro symmetry.
No, but I think what's important is that No, here I'm in 4D, and 4D is special in the sense that you have a stress tensor, and you have local conformal symmetry. I mean, from the shadow transform of the...
Exactly, but
Sorry.
you don't have in NED. Well, the soft theorems are there in NED, no? In a sense.
Yeah, but that's what I'm saying, is that even though the soft theorems are the same, the symmetry is not the same. If you have a local enhancement in 2D, doesn't mean you will have a local enhancement in
No,
higher
exactly. And then the question was, maybe this could explain why you don't have a Virasoro descendants or not, or you think it's completely out of. I know it was just to try to understand.
Yeah. Well, I think the question is exactly the same. That like if you're in 2D CFT, like you have the same symmetries, but it's just in 2D, it gets enhanced to local. So you have the symmetry. It's not that you don't have it, and the soft theorems sort of know about this.
But is the you see, when you speak about enhancement, it's also an infinite dimensional enhancement.
Yeah.
In higher dimensions, would it still be infinite dimensional?
No. There's no enhancement.
And so I think he is going in the direction, why do we expect these two things to be really related at a deep level and not just an accident, that they seem related? Because if you go into higher dimensions, there's not enough symmetry to justify.
But I think in higher dimensions, if we want to work out the OPEs, they will look maybe different than the OPEs in 2 dimensions.
You think they will be completely different, so we cannot
Maybe, yeah. This is what I expected, but turned out that's not the case. So one resolution would be like if we include these at 0 dependencies, then we will get the whole, Virasoro descendants or even BMS descendants, because you also have those in our celestial CFT. Like BMS is a symmetry of celestial CFT. So, yeah, I'm afraid this is still under work in progress, so we don't understand everything.
So how do you interpret the absence of Virasoro generators? What's your interpretation of that? Virasoro descendant, I mean.
Yeah, I don't have one. I think, so I'm hoping that, indeed, as I said, when we include the Z0 dependence, like we study for the entire tower, that the Virasoro descendants will be there. Or, when I say Virasoro, I also mean like maybe not Virasoro, but these W1 plus infinity descendants. Because this theory has this symmetry. And yeah. So it should appear in the OPE. Yeah.
Yeah. So the third line you have is quadratic in O.
Well, it's this normal ordered product operator that appears. No, I think so the spectrum will be of these two operators will cover this operator, so this primary with the descendants. But other primaries can appear at subleading order. And this is the case because we have like this definition of the normal ordered product that appears at subleading order.
But I'm worried it's not linear. It's not a single operator. It's usually a product.
Yeah, but this you can define. I mean, it's a primary of your. It's a primary of. It can be. Yeah. Yeah.
Maybe a question from an outsider. Can you comment more on the fact that you said you had a non-unitary CFT and the origin for that? I mean,
the origin of my comment is so I have to say some works have been being done about like the unitarity of celestial CFT and devising these other types of optical theorems and stuff like that. But my understanding is this. So what I mean by it's non-unitary is in the sense that usually in unitary CFTs you have this condition that if you take L-1 dagger, it will be L1, I guess. I think. Is that true? So that's in usual CFTs, or like more generally, if you take L-n dagger is just Ln, and then you can, and this is what gives actually the condition that primary descendants are null states, right? So because if you take L-1 times the state, which has a specific H and H bar, and if you compute its norm and it's a primary descendant, then it's annihilated by L1 and L-1, then it's 0. But so if you demand unitarity in the bulk, so because you can relate Lorentz transformations to these generators, right? Like there's a way to write down from the Lorentz generators the two copies of SL2C, SL2R on the CFT side. And if you demand that these Lorentz transformations are unitary, then you get other types of like Hermitian conjugate relations, namely one where L-n dagger is equal to L bar n. So this is by demanding Lorentz that Lorentz symmetry be unitary in the bulk. So if you want unitarity in the bulk, you will not get it on the boundary in this sense. And yeah, of course. I mean, yeah, indeed, that's true. Yeah, and 2, 2 signature. I mean, yeah, you can't talk about unitarity in a Euclidean context. Yeah. Yeah, this. Sorry? Yeah. It means Euclidean on the boundary. Yeah. Yeah.
Usually OPE is defined for thinking of unitary CFT
Yeah.
in 2,2. So okay, sector exists because
Yeah.
we computed it, but what can we say?
Why? So in unitary theories. No, I think we showed. So if you want to get a double pole, this would be equivalent to inserting. So here we know that there's only a single pole because if you insert two of these operators, sorry. Sorry, I'm just thinking about something, and we know that there's a single pole because this is Weinberg's soft graviton theorem, right? Like you only have the most singularity you can have is like with this 1 over p dot q, and this is sorry. Yeah, I'm looking at only the soft modes. Of course, like I'm not talking about any hard or. Yeah. Yeah.
And it's very basic. Here you start with S matrix elements, right?
Yeah.
And then you do a Millet transform.
Yeah.
So how do we know that that
Yeah, that's why. That's what the original motivation for us to study the OPE, because with this explicit form of the soft factor, you can literally just expand the double soft factors and look at the terms and interpret them in terms of like these operators. So indeed, like studying the full OPE gives us answer to these sort of questions. So that was original. Okay. So at one loop, yeah, I don't know. This is all tree level. And even the soft factor, like, yeah, and another thing I could add to the outlook is taking this double, like, how does the soft factor get modified at loop order with these log soft theorems, for example, etc. And what can we say there about, you know, the W1 plus infinity symmetry and like the regular terms, etc. So that's, yeah.
Any more questions? If not, maybe let's thank
Thank you.